So now we're going to kind of switch gears, and we're going to go to look at conventional gas, dry gas engineering. And we're only going to talk about the main, kind of the main topics that are relevant to understanding what's the difference between gas condensate and dry gas engineering. And that the last session today is going to exactly, we're going to talk about dry gas the rest of this session and the next session. And then we're going to, the last session, we're going to talk about, so what do we need to alter with the dry gas engineering to handle gas condensates? Material balance, rate equation, okay? That's what we're going to talk about the rest of the day. And then we'll get into the gory details Wednesday and Thursday on the details of those changes that are required. But we need to, I think, to have some basis in this conventional dry gas engineering first. So there'll be three things we look at. It'll be what I call the gas, the reservoir gas rate equation. Reservoir gas rate equation. Some people will call that an IPR, though conventionally IPR, inflow performance relation, is thought of together with oil, but it's kind of an IPR. It's and then Mike Petkovich would call this the reservoir back pressure equation. Okay. Then we'll briefly look at the tubing gas rate equation. Basically, we're getting how does the flowing gas rate vary as a function of average reservoir pressure and flowing bottom hole pressure. And here, the tubing gas rate equation is that how you get that same rate to flow through the pipe. So it's a function of the flowing bottom hole pressure and the surface flowing tubing pressure. Okay. And then we'll briefly, ever so briefly, combine the reservoir and tubing gas rate equations. To get what Mike Petkovich, actually the whole ex-Phillips kind of people would call just wellhead back pressure equation or performance. And then we'll look at the gas material balance. Very, very briefly, just the straight line, simple straight line using so-called P over Z versus cumulative gas production. Is it average reservoir conditions, cumulative gas production? That's just the integral of QG dt from time zero. And we'll look at briefly at the effect of aquifer performance on the material balance. And what the gas material balance basically gives us is what? It gives us how the average reservoir pressure varies as a function of how much gas has been taken out. Okay. So it's depletion. And then if we combine the rate equations and the material balance, that allows us to generate rate production profiles, rate production forecasting. And that can be for wells individually and the entire field for one or more reservoirs. And then ever so briefly, we're going to mention something referred to as layered no crossflow. This is again a topic from Mike Petkovich and his group. Layer no crossflow behavior. So individual wells are producing from from two or more what I call reservoir flow units. The reservoir flow units could be two layers that are not communicating. It could be two fault blocks that are not communicating in a horizontal well. So each reservoir flow unit has its own material balance that's independent of the other one. But the well is connected to two or more of these reservoir flow units. So two or more what I call reservoir flow units are connected to a well. So this would be something like M-BAL, where you got multiple material balances. Some wells can be connected to the multiple material balances. So with each with its material balance. Okay. So it's quite a bit of material to go through, but I think we'll make it through just being kind of first order, getting the first order things right, what's important, how do we do these things, and then we'll be ready towards the end of the day to go back and say, okay, so what's different about gas condensates in this equation, that equation, this performance, and so forth. And that'll be the starting point for tomorrow's discussion of condensate blockage, because certainly the reservoir gas rate equation is what's going to be affected. Okay. Now, as you know, we're going to go through this very quickly, and hopefully you'll get the highlights. But if you want to do some kind of a self-study on this, these e-notes are exactly giving you details, access to a lot of the information that we're going to go through very quickly. It's got the reservoir rate equation, tubing rate equation, water influx, material balance, field development, that's production forecasting, PVT. So there's a lot of background material there for details. Okay. What is the lunch break time?
In 15 minutes.
Okay. So that'll get us started. Okay. So the reservoir gas rate equation. So it's gas. I'm going to write it just like this, but what we really mean by this is it's the gas product, G hat. It's surface gas rate, because none of the books write it with the G hat, but this is just to remind you, is going to be equal to there's really two forms of the equation, but I'm going to start with this one. C, a constant, times the integral of the gas mobility, which is a function of pressure, dP from the flowing bottom hole pressure to the average volumetric pressure of the drainage area. And C contains, what it contains mostly is the KH product and well geometry stuff. So that's typically log RERW. You might have a -3/4, whatever, but basically that's usually that. And then skin. That can be damaged skin, stimulation skin, which is kind of a geometry. If you have a hydraulic fracture, that's a well geometry skin. So that would be part of the well geometry, so to speak. Skin. Okay, so that's pretty much it. And the normal equation for C is, if we use, is basically KH over log RERW -3/4 plus S. Okay, I think somebody's got their microphone on. I'm not sure. Okay. Now this is all based on Darcy. This is based on the Darcy equation. There's another form of this, which is the Forsheimer. We'll come back to that, but okay. And the mobility of gas is basically 1 over mu G BG. Okay. Or we use P over mu G ZG. These are the same things because BG is just okay. So that's the definition of BG. So they're basically the same thing. There's a constant, you know, you got the PSE, TSE, TR. I mean, there's stuff in there, but and I'm not dealing with units either. I'm not going to give you I could give you the one for field units, but I'm not going to mess with that. We're just looking at concepts here. So sometimes people write the lambda G as 1 over mu G BG, and other times it's P over mu Z. It's the same thing. So what does that pressure-dependent mobility look like for gas? Okay. So it's basically linear function up to about well, it's going to turn over, and then it's going to kind of reach a maximum, and then it'll very ever so slightly kind of go downwards, more or less constant. Every gas will look like this. Okay, and of course sometimes, like that gives an example, it says that, well, you can approximate this as I'm going to take it away, but you could approximate this as just a straight line, goes up like that, and then it goes flat. You get the same area, but not quite. Okay, as an approximation. Okay. I'm going to take that away just for the sake of make this less messy. So let me just take that part away. Okay, so we'll be back to our. So if you have the average reservoir pressure, let's say out here, at some point in time, then and the flowing bottom hole pressure down here, then it's just the area under this curve. That's the integral. Okay. That area times the C is giving you the rate. And of course, there's the guys, it was Al-Husseini, Ramey, and Crawford, I think, 60s, 70s, I don't remember when, introduced what was originally called the gas pseudo-pressure function, M of P, which has now been replaced by the symbol pseudo-pressure function, and it's defined as 2 integral P over mu Z dP from any reference pressure. You can use atmospheric, 0, whatever you want, to P. So that's this function here. So that would be the area starting from 0, the total area here, and then minus this. So basically, so if you have PWF to P average of this term, that's just 0 to PR minus 0 to PWF. And so that is make this lime green and make this one orange, not orange, but dark green. Okay. So the area, the dark green area, is this entire area here. And the lime green is this area here. Okay. So that gives you the term to multiply by the C. And so one pre-calculates this, you pre-calculate this once and for all, pre-calculated once for the entire reservoir, the entire gas reservoir, used for every well. Okay, so you have this pseudo pressure function, and it's in there, and you just put in the PWF and PR, you interpolate, this function. So you basically create this PP as a function of P table or equation. Now, none of this is really irrelevant. The main thing is the shape of it that we're looking at. Okay? Any questions? Let's So when we start talking about gas condensates, what we're going to see is that you can use exactly the same equation, and the only thing that changes is this area function. The lambda function is going to change in a way that we're going to look at later today, but it's going to get less. It's going to get smaller in a certain way. So we need to understand how that's going to become smaller. Okay? And that's the only change. The C is still going to contain all of the constants. KH is a constant. The well geometry is a constant. If it's stimulated, horizontal, multifracture stimulated, skin, damage, that all stays the same. Doesn't change at all. That's what Favong Whitson paper shows. The only thing that changes is the area under the curve. And we have to figure out how that changes. Okay? Okay. And then I'll just mention that the other form of this, which can't be ignored, is the Forsheimer equation. And you end up with well, there's a couple ways to write it, but the easiest way to write it is QG is equal to P pseudopressure. I just call it R minus P pseudopressure WF. P pseudopressure R is just P pseudopressure evaluated at PR, and P pseudopressure WF is just pseudopressure evaluated PWF. Okay. I know there's a lot of nomenclature here, but it just makes it so. That, and you got our KH, we got our log RERW minus 3/4. It's all the same. Don't need that. And then you've got plus S skin. And then you've got an extra term here. This is the only thing that changes for the Forsheimer. It's called D, but then you put the Q down here. Now you got Q on the left-hand side and the right-hand side. And this whole term here is referred to as the total skin, which is rate dependent. Rate dependent total skin. Rate dependent total skin. And it's usually determined by well testing. So they do well testing with different rates. They interpretate the KH should always be the same for each rate. It's not always that the case, but the KH should be the same all the time. And they get skin from the well test. Okay. And they plot it versus rate, 0, 0. And here we get, that's 0 rate, that's this term right there. And then they get things like that. And of course, why those don't intercept where I want it to intercept. Move it up a little bit. Okay. So those are for the 4 different tests. And then we draw a line through them like that. And the slope of that line is D. So nothing else changes. So now that whole equation can be rewritten as, I never get it right, but it can be rewritten as I think it's B Q G squared plus A Q G minus equals 0. Can be written as a quadratic equation in rate. I'll let you do the algebra, but that's basically it. So this A has, the KH and the skin term, and the B contains this D term. Okay? So if you're just drilling at the mouth for lunch, you're going to get it here in a minute. But if you're drilling at the mouth, seeing what it looks like in terms of an IPR plot, because you're an oil engineer and you don't understand all these things, then the IPR equation is plotted like this: PWF versus rate, where we've got P average there, we got a 0 rate when flowing bottom hole pressure is equal to that. And this basically will look something like this, kind of straight line there. As you go to the lower pressure, because of the area getting smaller and smaller as you go to lower pressures, it looks like that. This is just say that we have a D of 0. We don't have any non-Darcy effect. And this, if you add the Darcy, the non-Darcy D greater than 0, saying that you have turbulent flow, particularly near the wellbore, then you're going to get something that looks very similar, but it's going to be going down even further. Like that. Okay. So that's going to be D. And then if you worked for Phillips Petroleum Company, you would not be allowed to draw it this way. You would draw what's called the back pressure equation instead. And there it's using a log-log plot where it's basically P pseudopressure R minus P pseudopressure WF on a log-log scale. I don't know what the units are going to be. They're big numbers, but 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, depending on the units, of course. And then you've got 100, 10, 1, 0.1 gas rate in million standard cubic feet per day. And the Darcy equation is going to look something like this. Okay, and that's going to be, you're going to put a little hat there. And this line here will be used from time 0 forever on this well in the Phillips. Whereas here, if you're using Prosper, every time the reservoir depletes, you've got to redraw these lines Okay. And um, and if you have d greater than 0, then this line is going to be looking like this. And also, you only have to draw this once. Okay. That same line will apply to the well throughout its life. So here in this back pressure plot, the curves never change. If you plot it in terms of an IPR, you have to replot it every time the average reservoir pressure changes. And the slope of this line here is 1. And the slope of this line here is greater than 1. And could approach 2 in an extreme case. You know, if the D is large enough, then the slope, particularly up here at the top, you see it's increasing, could approach 2. Slope could approach 2 at a maximum. But as you go to low enough rates, then the slope, it coincides with the slope of 1. Okay? So I think that's a good place to stop.